And this is to reduce the amount of single-stranded DNA, which is much more prone to chromosome breakage than is double-stranded DNA. Now, there's two different types of DNA polymerases acting at this time. One is called the leading strand DNA polymerase, and it acts by extending the leading strand DNA towards the unreplicated DNA, or in the same direction as the overall DNA replication process. So this is very easy to understand. It's going to follow right behind the unreplicated and double-stranded form of the DNA. In contrast, replication of the opposite strand has to move in the opposite direction, away from the direction of the overall fork movement or replication. And so in this instance, the primers will be formed, and the polymerase will move away from the overall unreplicated DNA and in the opposite direction of the fork movement. Now, these two events are happening simultaneously at the replication fork, as is illustrated here. And you can see that the lagging strand DNA polymerase is moving in one direction, the leading strand is moving in the opposite direction. And when you finish an Okazaki fragment, as these smaller fragments that are made on the lagging strand are called, you then reposition the polymerase and start a new Okazaki fragment. And eventually, at the end of the replication process, these primers that are used, which I'll have more to say about in a moment, have to be removed and the DNA linked together to form a continuous strand, unlike the leading strand where it is continuously synthesized. Now, one property of DNA polymerases, all DNA polymerases, is that they cannot start a new DNA strand by joining two deoxynucleotide triphosphates. They have to have a primer in the form of a primer template junction. And so in order to initiate the new strands that are required for the replication process, we need a different enzyme called DNA primase. And what DNA primase does is it synthesizes RNA primers. And this is because, unlike DNA polymerases, RNA polymerase, of which DNA primase is a specialized form of, can take two ribonucleotides and initiate a new strand of DNA. Okay. Now, importantly, once it does this, it can be extended by the DNA polymerase, basically forming a primer template junction. And one interesting property of the DNA primase in E. coli is that it is stimulated to act by interacting with another important protein that acts at the replication fork called the DNA helicase. Now, replicative DNA helicases always come in the form of hexameric ring-shaped structures, as you see here. Okay? And these hexameric ring-shaped structures will encircle one of the two strands of the DNA, and they will then move in an ATP binding and ATP hydrolysis dependent fashion in a defined direction along this single-stranded DNA, and by doing so, they will displace the other strand of DNA. So you can see that here with the helicase unwinding the DNA. Now, I've looped this, so you'll see it a few times, but I want to point out also that the direction that a helicase moves on its encircled strand is a property of the helicase. And in this particular case, I've illustrated the E. coli replicative DNA helicase called DNAD, and its polarity, as this property is called, is in the 5' to 3' direction. So you can see it's starting at the 5' end and moving towards the 3' end of the DNA. Now, we've talked about a number of proteins that are involved at this point, but one that is not an enzyme, unlike the ones we've talked about thus far, has a primary role of holding the two strands apart after you unwind. Because, of course, these two strands of DNA that I have over here are, in fact, complementary to one another and can rapidly reanneal. Now, this is prevented by two different events. The first one is simple to understand. That is that the leading strand DNA polymerase up here at the top follows almost directly behind the helicase. And so that single-stranded DNA is very rapidly converted into double-stranded DNA. And this prevents it from annealing with the complementary lagging strand template. Now, there's another concern, however, which is that the lagging strand template will anneal on itself. And so there are a specific set of proteins called single-stranded DNA binding proteins, or SSBs, that will bind the single-stranded region of the lagging template and hold it in a single-stranded state, preventing it from annealing to itself. And what's important about this is not only does it keep it from reannealing, but when a DNA polymerase approaches a region of single-stranded DNA bound by the SSB, it is readily displaced, allowing the template that's left behind to be readily replicated by the polymerase. Okay, so we talked about the leading and lagging polymerases, but it turns out at the replication fork, they are part of a larger complex called the holoenzyme, in particular called the DNA polymerase III holoenzyme, which is a very specialized form of the DNA polymerase for acting at chromosomal DNA replication forks. So it's illustrated here, and there are several parts to this complex. So first, there are 3 copies of